Hi class, so we have already have a look at this auto cycle. In this video, I'm going to proceed with this cycle example. So let's have a look at what we have in here, right? It says that an ideal diesel cycle has compression ratio of 17 and a cut-off ratio of 1.3. So we have this is your compression ratio, which is your RV, and you have a cut-off ratio, which is your beta. At the beginning of the compression process, the temperature and pressure of the air are given 37 degrees C and 100 kilopascal. So this is 37 and 100 is the value at your state 1, because it says here beginning of the compression process. And if the mass of air is given 0.1 kilos, you need to show all the process on a PV diagram. And you have to determine all the temperature and pressure at the end of each process, the heat addition during the constant pressure process, because this is an ideal diesel cycle. So the combustions happen during the constant pressure process, right? Next, we are looking for your work net, and then count for your thermal efficiency, and finally we are going to find your MEP, mean effective pressure. So you will see the steps is about the same with your auto cycle, where you need to find the heat addition, and then you get your work net, and then you calculate for your thermal efficiency, and finally you got your MEP. But the difference will be on your PV diagram and this cut-off ratio over here, right? So we are going to solve it. I'm going to show you on how to solve it step by step. So first, let's plot the PV diagram of this diesel cycle. So you have a pressure versus your volume here, and because this is a diesel cycle, so you are going to have heat addition at constant pressure, and your exhaust gas will be at constant volume. So you're going to connect this process, right? So this will be your state 1, where the compression is happening. This is your state 2, this is your 3, and this is your 4. So this is your Q in, where the combustion is taking place at constant pressure, and this is your Q out. So if we recall back from the video explanation on your diesel cycle, so this heat addition here is happening at constant pressure. So you will see that this is where your combustion process takes place. So as the combustion continues from beginning up to this volume, so this piston cylinder are going downwards. That's why you have the changes of volume in here, right? So the combustion will stop once it reached once it already fully combusted. So this is where the combustion process stop, and this V3 over V2 is what we name it as cut-off ratio, where this is the maximum volume when the combustion process stops. And this is where the exhaust gas being out of your piston cylinder, getting out of your piston cylinder. So this process is happening at your constant volume over here. So given the compression ratio as 17 and your beta is 1.3, and P1 and T1 is 100 and 310 Kelvin, this one is already changed into Kelvin. So we are going to solve this step by step with assumption of constant heat value. Alright, so state 1 to state 2 is your isentropic compression process. So we are going to make use of these equations of isentropic for ideal gas. So you make use of the between temperature and volume relations. So you will have your temperature at 2 here. Next, we are going to make use of this pressure and volume relation so that we will obtain P2, right? Because the first question is asking you to find all the temperature and pressure at the end of each process. So you make use of this pressure and compression ratio relations, then you will obtain your pressure at 2. Next, we will continue the process from state 2 to state 3. So state 2 to 3 is your heat addition at constant pressure, right? We will make use the PV-MRT relations. So you rearrange these PV-MRT relations into this pressure constant, which is P3 must be equal to your P2. So you rearrange this PV-MRT over here and over here. Your MR can be cancelled out because this is closed system, so your mass is constant, and we are going to use R as the same. So left with you T3 over V3 is equal to T2 over V2. And this V3 over V2 here, right, V3 over V2 here is actually your cut-off ratio. Okay, so you just substitute this 1.3 into here. T2 is already, you already have the answers for T2, and finally you will get your T3. So this is the value of your T2, your T3. Your P3 is actually the same with your P2 as you obtained previously. So next we are going to proceed with the expansion cycle over here, 3 to 4. By now we already obtained the value at state 2 and state 3. 1 is already given to you. So in this case, your state 4 over here have two relations. One is the relation between 3 and 4, which is this process is an isentropic expansion, and the other one is between 4 and 1, which is this is the process of heat rejection at constant volume. So in order to find 4, you can make use of these relations, or you can pick with these relations over here. So let's say if I choose to make use of this relation at constant volume over here in order to obtain your state 4. So state 4 to 1 is your heat rejection at constant volume. So V4 is equal to your V1. So we rearrange your PV MRT, so it's going to be MRT4 over your P4 is equal to MRT1 over your P1. And you cancel out the MR term. So let's say in this case we are trying to look for your temperature first. So it's going to be your T4 is equal to P4 over your P1 times with your T1. Alright, so let's have a look at the what is the unknown value that we have in these equations, right? So P1 is already given to you and T1 is already given to you. So you need to solve for your T4. Unfortunately, you don't have your pressure at 4, right? So your pressure at 4 is at this value. So you already have your P2, which is equal to P3, and P1 in here is already given, right? So this is in the case of if you make use of a relation between 4 to 1. So let's have a look if you make use of the relations of isentropic expansion between 3 to 4. So state 3 to 4 is your isentropic expansion, so we are going to make use of these relations over here. Alright, so if you make use of your isentropic expansion relations, so you are going to need your V3 over V4 here, right? And we are going to find out what is V3 over V4 by using these relations of compression ratio and also your cutoff ratio. So you are looking for your V3 over V4, and we have V3 over V2, right? And we need, in order to obtain this V3, right, over V4, so we need to get rid of this V2, right? So we have this V2 in your compression ratio over here, and please note that your V1 is actually equal to your V4. So let's say if we change this V2, sorry, let's say if we change this V1 here into V4, right? So we are going to have your V4 over your V2. Okay, but we need your V4 at the bottom here, the denominator. So therefore we are going to times with this inverse of your V4 over V2. Alright, so now it's going to be inverse, so therefore it will be times with your V2 over V4, or V3 over V2 is actually your beta, times with your V2 over V4 is actually 1 over your RV, or your compression ratio, right? So once you get the value, so you can substitute into these equations. T3 is already, you already find what is the value of T3, and finally you will get your T4. So now you have already obtained your temperature 4 here. So when you want to find your pressure at 4, right? When you want to find your pressure at 4, you can make use of these equations, or also you can make use of the previous equations that you got from these constant volume relations, right? So let's say you want to find your P4 by using this constant volume relation. So you need to change a bit the arrangement over here, because you are trying to look for your P4 now. So you substitute all the values, right, in here, and finally you will get your pressure at 4 to be 144.41 kilopascal. So you can check on the value that you got, right? So P1, your P1 is actually at 100 kilopascal. Your P4 is about 144, and this P2, P3 is about 5000 kilopascal. Now that you get all the values for your T1 up until T4, so you can complete the rest of the question here. Alright, so now that you have all the values of the temperature that you need at all states, right? So let's solve for the B part. So Q in is the process is happening at constant pressure, right? In between 3 and 2. So you make use of this equation. Finally, you will get your Q in is equal to 290.28 kilojoule per kg. Now the question is asking you in kilojoule, right? And already given to your mass, which is 0.1. So your Q in is actually 0.1 times with your 290.28. So finally you will get 29.03 kilojoule. Next is to find your work net, which is work net is happening between your Q in minus your Q out. So you already got your Q in, now is to find out what is the value of your Q out. So your Q out is equal to, because the process is happening at constant volume, so you're going to times with your CV, and not to forget your mass. So finally you will have about 9.88 kilojoule. So you can find your work net. So your work net will be 19.15 kilojoule. So next is to find your thermal efficiency, which is your thermal efficiency is actually work net over your Q in, or you can make use of 1 minus your Q out over your Q in, and don't forget to times it with 100, because we are talking about efficiency, so it should be left in percentage. So you make use of either this one or this one and times with 100, so finally you will get your thermal efficiency to be 95.97%. Next is to find your MEP, which is equal to your work net over with your change of volume, or work net is actually over your V2 minus your V1. Your V maximum, which is 1, minus your V minimum, which is 2. Or also you can make use your work net over V1 1 minus 1 over your RV, right? You can make use either one. It's either this one or this one. If you are using this one, so you need to find a volume each. If you are going to use this one, you only need to find the volume at 1. So let's say we make use of this one, so we need to find your V1 first. So we make use of your PVMRT. Therefore, you will obtain your V1. Which is equal to 0.089 meter cube. So you substitute into this equation, finally you will obtain your mean effective pressure to be 228.62 kilopascal. So now you have already completed all A until E. Next we are going to have a dual cycle, which is the combination of diesel and auto. Thank you.